Module 0.2 in the Intro to C Programming course will provide a little bit of motivation for why learning C is important. So let's start off with a little bit of history. The C programming language was originally created in the early 1970s. This was done as an industrial effort to create a very general purpose and very useful programming language that a lot of rising programmers or rising developers would use in industry. It was built off of some existing programming languages. The name C is because languages were just labeled alphabetically, so C came after B, which was a variant of a language called the Basic Combined Programming Language. The creation of the C programming language is often attributed to Dennis Ritchie, who was working at Bell Labs at the time. Many people were involved in the creation of the C programming language. And the original design of C actually targets low-level system functionality because at the time, in the early 1970s, a lot of what was being done was design of initial computing systems and the operating systems that ran them. So the C programming language was really designed to target the low-level system functionality that is used for all of the tasks that an operating system will do to provide support for user applications. So this includes things like managing the contents of memory, directly controlling the processing unit within the computer, providing services within the operating system, managing files, running applications, all of the other things that are involved within an operating system. And so C was actually an integral part of creating the Unix operating system back in the 1970s. So a lot of people might ask, why are we interested in learning a language that's been around for this long? It's been over 50 years since Unix was created and since C was designed. Why are we still using this language? Well, it turns out there are a lot of reasons why people still learn C. The first one is it is a foundational language. It's used in a lot of different places. It is still used a lot, and part of the reason it's still used a lot is because it's designed to be very powerful. It's designed to be very general purpose. And at the same time, it's designed to be very fast and actually relatively simple. You can do a lot of complex and powerful things with C, but the language itself is relatively straightforward to the point that we can learn everything we need to learn in a couple of dozen videos. So the other nice thing about learning C is it is one of the foundational languages, and if you know C decently well, it really helps to pick up other modern languages, newer languages. And again, part of the reason for learning C is a lot of operating systems still use it. Most Unix variants, most commercial Unix variants, and open source Linux variants are mostly written in C and languages that look a lot like C. So if you know C, it gives you a lot of opportunity to do things within computing systems. If you're curious to see sort of the evolution of the popularity of C in relation to other languages, there is a link there to a website that tracks the popularity of different languages, and you'll see over those 50 years, C has actually remained among the most popular languages for the majority of that time. So since we're talking about computing systems, it's important to know that many of the main benefits of the C programming language are basically its ability to do things at a very low level. It's a very powerful language. It allows you to directly control computing system. It allows you to directly control hardware. It allows you to directly interact with peripherals, to manipulate memory, to change files. It's a very powerful tool. And in some ways, this is also what makes it a little bit dangerous. C is known for being a language that is not very safe. And these two things go hand in hand. Something that gives you a lot of power and a lot of control gives you a lot of opportunity for making mistakes. So in order to really fully understand and appreciate the C programming language, we actually have to sort of think about things system-wide. We can't just think about writing applications. We can't just think about writing code. We have to think about how the code operates and how it interacts with the system so that we can avoid some of those dangers and some of those pitfalls. So one important thing that doesn't often come up in intro programming courses is programming is not just about writing applications. A lot of people who write programs are building applications. A lot of people are application developers. But there is a lot of code writing. There are a lot of programs that are doing things at much lower levels within a computing system. And to really get the full context of why C is very useful, we have to actually understand things at the system level. So this leads us to what is called system programming. So C can be used for writing software applications, but in many people's minds, it is better suited for system programming. So let's take a deeper dive and look a little bit at what is system programming and why do we actually have to think about the system beyond just the program. So to give a little bit of an introduction to how computing systems work, sort of the 30,000 foot view of computing systems, within a computing system, the part that humans actually interact with is typically application software. Applications are the highest level of abstraction that humans interact with, and typically applications are hardware agnostic or platform agnostic, meaning that a piece of software will run on any generic computing platform within reason. And these are pieces of software, or these are pieces of code that provide services to users. Below the applications, we have a fair amount of abstraction. If we want to be able to write software that doesn't depend on the platform hardware, we need what's called an abstraction layer. Abstraction layers show up in a lot of different places. These are very popular in computer science. One of the main forms of abstraction layer that you'll see in writing code is you will actually see things like libraries and things like programming interfaces that an operating system exposes to allow a piece of software to perform some sort of functionality without caring about how the operating system actually does the job, without actually caring how the hardware is working, without caring what peripherals are being used, what resources are being used. So this abstraction layer allows the software to not have to care. And this is great if you're writing high-level applications. This is not necessarily great if you're trying to do things at very low levels within the computing platform. So below this abstraction layer, we have the software that is actually doing the work underneath. We have the system software, we have services that are interacting with hardware, we have drivers that are interacting with peripherals, and below that we have the actual system hardware itself. So we can think of this as the software that lives below the abstraction layer is performing services to manipulate the hardware, and it actually will do that independent of what applications are trying to do. So the system software is typically application agnostic, meaning it doesn't care why it's being asked to perform a particular job, it's just doing the job that it's designed to do. And this will typically involve interacting with the processor, the CPU, the memory, whether it's temporal memory and RAM or persistent memory stored on a disk somewhere, and also perform a variety of input-output operations, things like playing music, listening from a microphone, recording video from a webcam. These are all simple examples of I/O that directly involve hardware. And so you can see how the system software plays a crucial role in the job that the operating system is performing in order to provide the abstraction layer that the application software is using. So in some sense, system programming is just the kind of programming that involves creating the system software, writing those services, writing those drivers, and providing the foundations of what the computing system is doing. In other words, it's not writing applications, it's writing services to make the system usable by the applications. So the role of C can actually be multiple different things. We can come up with scenarios where, yes, we actually want to use C to write application software. We can also come up with a wide variety of scenarios where we want to use C to write system-level software, drivers or services. And we can also imagine using C to write the abstraction layer itself, the interaction between the application software and system software. We can use C for all of these things. It might not be the best choice for all of them. It kind of depends on what we're trying to do with it and what the other options are. But in many cases, it may be a viable option. Particularly when we're looking at system software, C is still a very popular choice. And this is where a lot of C programming is still done. Because it is a low level, there is a low level of abstraction in the C language, and it can directly interact with system resources, it's a very popular choice for doing system programming. It's not the only choice, but it's still very popular because it is general purpose, it's very powerful, and it's been around for a long time. People understand it very well. Now, the C language has changed quite a lot over the years that it's been around. What we're going to cover in this course is primarily going to be the foundational parts of the C language. We'll talk a little bit about some of the extensions that exist, but we're going to focus on the primary foundational materials. So keep in mind that as the language has evolved, it has added a lot of capability. In some places it has removed some capability. We'll talk about those things here and there. So it also turns out that C is sometimes a popular choice for creating abstraction layers, mainly in the forms of creating what are called system calls, the function calls that applications can make to request services from a system, from an application, for what is called a hardware abstraction layer, which is where a piece of software presents the capabilities of a piece of hardware through a system, through a series of programming interfaces. And this starts to look like a driver API, where a piece of software can control a piece of hardware, request input, request output. This is where C is very, very popular. So the approach that we're going to take is we're going to approach the C language fairly generically. We're going to try to cover most of what's needed to be able to either approach application programming or interface design or system programming in C. In some particular topics, we'll go into more detail on the system side. In others, we'll go into more things that are more relevant to the application side. So for example, when we start talking about low-level memory manipulation, that's definitely something that application programmers don't want to have to do. That's more of a system programming thing. When we talk more about data manipulation, that's more of something that applications are going to want to do. So we'll talk about both of these and try to do that relatively generically so that you get the value on all fronts. So in order to do this, as I mentioned, this course is going to be relatively hands-on. There are going to be programming tasks. The next video is going to focus on walking you through how to set up an actual programming environment to use for those programming tasks.